Hello. This video is going to be about using symbolic processing to find the gains for a lead lag filter, and I want to show why it's superior to using Root Locus, and it's also much simpler. So to start with, I'm going to show you the open loop plant. This is it. Now this is actually like a motor, where this is the gain and this is a corner frequency. And this part here with the alpha over S plus alpha, that would be how the motor would get up to the velocity. The Ka is the gain, and that is multiplied by the control output to figure out what the final speed is going to be. And then this S integrates velocity into position. So for instance, Ka, the gain, open loop gain, would have units like millimeters per second per percent control output. And to relate that to the video that I'm critiquing, this is the open loop transfer function that was used. And she didn't say much about where these numbers come from. But again, this is a corner frequency. And then this 5 is the product of the open loop gain times the corner frequency. So a gain of uh, 1/4 of a millimeter per percent output means that at fastest, if you output 100%, you'd only go 25 millimeters per second, which isn't very fast. The controller is, this is a lead or a lag filter. We don't know which yet because we don't know what the zero and the poles happen, where they happen to be. This is a controller gain. And what I'm using is this equation here for the closed loop transfer function. So I have the gain of the actuator and the gain of the controller over 1 plus the gain of the actuator times the gain of the controller. And if I substitute these functions, transfer functions, into this formula, I get this. And if I simplify this equation, and this gets a little messy, so I use MathCAD for it. And you could use other things like Mathematica, WX Maxima, SymPy, or such. Then what ends up happening is that you get a transfer function that looks like this. And this is simplified. And the big thing is that this is the characteristic equation, the open loop characteristic equation. Or no, it's closed loop, obviously, because there's gains here. But it's the characteristic equation that you have to work with. And this is the desired characteristic equation. And what I desire is to place 3 closed loop poles at minus lambda. So to do that, what we do is we get the coefficients for each power of S. So we have, for instance, let's just scroll down here a little bit. These are the coefficients for the current system. And then these are the coefficients for the desired characteristic equation. And what we need to do is equate them. In other words, we equate this lambda to the third power to this, and this to this, and this to this. And we have 3 equations, and we have 3 unknowns, which are Kc, which is a controller gain, and the pole, and then the 0 for the controller. So let's just scroll down and see how that's done. So here is where I equate, and then I can solve for the controller gain, the pole, and the 0, and these are the equations. So this is the gain, pole, and 0. And I could stop here because I've got it solved for all time, and I will never have to mess with root locus, because as long as I know what the how I want to place the closed loop poles, and I already have the actuator gain in alpha, which is supplied by the original problem or a system identification, then I can just use this formula to figure out what the gains are going to be. So you can stop right here, but I'm going to show you more. I've got another way of doing it. It's called direct synthesis. And basically, this is the same thing down to here. And what I'm doing is I'm solving for the controller gain. from this equation, solve for the controller gain or the controller transfer function. And if I have the controller transfer function and I'm solving for the controller transfer function, and I substitute the transfer function for the plant and my desired characteristic equation or response, then I can simplify, and this is the resulting controller. Now, this is my desired response, and what I've done is I've simplified the system from a 3-pole response down to a 2-pole response, and what I've done is I've used one pole to cancel the 0. So there's no 0 in the final transfer function, and there's just the open loop or the pole, and I mean the 0 and the pole, and then this lambda squared over k alpha times or ka times alpha is the gain. So this is the equation written out. And if I take this original equation for the closed loop transfer function and I simplify it, it actually simplifies down to this. And notice I've included the zeta, the damping ratio, and I'll get around to that in just a minute. So now that I have this equation, I can solve for it symbolically. I can do an inverse Laplace transfer function, and this is the results. And you can see there's sines and cosines, and because there's a zeta, if the zeta is not 1, then what happens is we'll have overshoot due to the cosines. If I set the damping factor to 1 and I do a step, see here I've substituted 1, then this is the final result, and it's just a nice exponential ramp up to the set point, which is R. So now the rest of this becomes pretty much the same between the two worksheets that I've made. I've set the gain. Remember, the gain is 1/4. This is the open loop gain. It's in millimeters per second per percent. So again, the max speed is 25 millimeters per second. This is the corner frequency. I just inverted this for the well, just for general information, but if you take 4 time constants, then you get a rise time about 0.2 seconds. That isn't really achievable in this system unless you're making a very small step, because the controller output will saturate. Now, you can use this equation to figure out, if you really want overshoot, you can use this equation to calculate out a damping ratio, but I want to have the damping ratio of 1, so there's no overshoot. Why have overshoot if you don't want it, don't need it? And then I'm setting the closed loop poles at minus 2 alpha, which is going to be at minus 40. See, so let's go on down. And then from those equations above for the controller gain and the pole and the 0, I use the values above, and I have these values for my gain, pole, and 0. And then something that the instructor didn't mention is that you can also use feed forwards. I'll show you how to use those later, but this is the velocity feed forward, which is just the inverse of the controller gain, and the acceleration feed forward gain is just 1 over the open loop gain times the corner frequency. And these are open loop gains. These won't change. They're only a function of the open loop transfer function, whereas these values will change if I change the value for lambda, which is where I want to place the closed loop poles. And obviously, if I move lambda closer or farther away to the negative real axis, then these gains are going to go up. So let's go on down. Now let's look at a real step response. Now this is a theoretical step response, and this is another thing, place where I have problems with instructors, because they'll go into MATLAB or something like that and they'll plot it out. And the problem with this is that it doesn't take into account that there's limitations on the control output. So here you can see that the rise time is about 0.2 seconds. Just let's go on down here, just as desired. Let's go on down. See the time scale? Okay, and I can do an inverse Laplace transfer function. And again, I have zeta set to 1. So what happens is I get an exponential type response. And I could have combined these exponential terms. And I have now a position. And I can take the derivative of this, and I have the velocity, and I can plot them out. And what's unrealistic about this is that to make one step, the control output, or to make a step of 1 millisecond, the control output will actually saturate. And what's kind of bogus is that if I set this to 10, you see it's still going to give me a response of 0.2 seconds. But what's very unrealistic is that if I were to do this on a real controller, it would be saturating at 100%, so it would take much longer than 0.2 seconds. And essentially, whenever you're saturated, you're running an open loop. So I'm just going to move this back. So let's see what it does in a more realistic simulation. And the instructor didn't cover this at all either, and I think it's important. I'm going to simulate a system, and I'm going to assume that I'm doing this for a motion controller. I have an update period of 1 millisecond. I've got a Z pole. This is a pole in the Z domain or discrete, and this is how you convert the poles in the S domain to the pole in the Z domain or discrete. And then this is how you convert the or scale the gain in the continuous domain over to the discrete. And then I have the state space. This is a corner frequency, and this is the numerator of the transfer function. And this equation here converts the continuous domains here, or arrays, into the discrete domain. So I have the discrete numbers here, and the instructor doesn't show you that. You assume that it's all being done automatically in MATLAB or whatever, but you know, in reality, you can't ship MATLAB along with your product. So now we're going to see how it actually responds. I'm going to start out at 0 velocity and 0 position, have the control output is 0, and my initial error is 0, and I have the target position or reference, the state, the control output, and the current error state, and I need that for doing the iterations. So the first thing I do is I take the control output and I multiply it by the input coupling matrix, and I have the state. I multiply it by the discrete transition matrix, and I get a new state. And then this is the error. This is how you implement the lead leg filter in discrete format. And then I have to return the new state, the new control output, and the new error. So now that I have that, I'm making a step to 1 millimeter and a step to minus 1 millimeter, and then I go back to 0, and this is executing the lead lag filter, and it does it n times, which in this case is, because I'm doing this every millisecond, 1 second. And this is my response, and you can see that it takes longer than 0.2 seconds. Now remember when I just did it using the time domain, you know, converting the Laplace transform, doing inverse, getting an equation in time, it took 0.2 seconds, but it takes a little bit longer in reality because you're saturating the control output here, and you don't get a chance to use the whole, well, it's limited to 100%. And if I were to make a step from 1 to minus 2 millimeters, or minus 1 millimeter, that's a step of 2 in the opposite direction, you can see that it saturates even more, and it takes more than 0.2 seconds to come down. because again, it's saturating. And this is what the instructors don't take into account. In reality, you have a controller that can output plus or minus, well, 100%, whatever that is, like plus or minus 20 milliamps or plus or minus 10 volts. And then it goes through some sort of amplifier or similar, and then you get an output, but you're limited by this plus or minus 100%. This is my velocity, and I just want to point out that, again, we're not making it in 0.2 seconds because we're in saturation. So now I'm going to use a more realistic example, because in motion controllers, you don't usually do step jumps because that causes, well, it causes sudden output to go to 100%, and that will cause a jerk. And if you're moving 40 tons of steel, you're going to get thrown out of the plant very quickly. So I'm going to do a nice smooth ramp. I'm going to move 10 millimeters in 1 second. I've got my velocity feed forwards, well, they're set to 0 right now. And this is like what I did above. Only thing is I've added the capability of doing feed forwards. So this is R, which is the target position, velocity, and acceleration. R1 is the velocity, R2 is the acceleration, and I'm multiplying by the velocity feed forwards and the acceleration feed forwards. But right now I have them set to 0, so we're not using feed forwards. But other than that, this is the same, and I'm taking the output and I'm limiting it to plus or minus 100%. But in this case, because I'm doing a smooth ramp, I don't ever saturate the system. So these, I mean, you should always have the plus or minus 100%, but they're not going to be reached in this case. So here you can see the response. The ramp I have it ramps up in 1/3 of a second, goes at a constant velocity for 1/3 of a second, then it ramps down. And you can see there's a huge following error. And I can decrease that following error in 2 ways. One is I can reduce it to 0 by using feed forwards, and as long as my model is correct, my feed forwards will be perfect, and they will follow right on. The target and the actual positions will be the same. So I'm going to just enable the feed forwards. So now I got my velocity feed forward and my acceleration feed forward, and you can see that it tracks perfectly. Come down here, and you can see it tracks perfectly. And because I'm moving at, you see the maximum velocity is, what is it, 15 inches a second. I need to have an output, or 15 millimeters per second. I have to go 60% output, because remember, you have 1/4 of whatever the output happens to be 60%. That will result in the velocity of 15 millimeters per second. So anyway, then this acceleration is a little bit harder to describe. You're just going to have to trust the math. But you can see that works out pretty nicely. Now let's take care of the lead and leg problem differently. Let's zero out the feed forwards again. Okay, so now they're back to 0. And we can reduce the error by changing the the lambda. So now it's set at minus 100. You can see this gain went from, what is it, 360, it goes up to 1000. So the gains have increased quite a bit, and the poles and the zeros have moved quite a bit further to the left. And you can see this is the new equation. I need to copy that into here to plot it properly. And this is old data. This is from before. But now we can see the control output. It still doesn't go up any faster. And the reason why is because the control output is saturated for a longer period of time. So that's what's wrong with a lot of these videos is they don't take into account there's a difference between the controller and the open loop system, and there's a limit on the 100% output. So if you don't have the system designed right, in other words, if I wanted to go faster, I would need to increase K from say 1/4 to 1, and then I would be able to go faster. But right now, my open loop transfer function or gain is only 1/4 of a millimeter per second per percent output. So let's come on down here and take a look at the following error. When I'm doing see, in this mode, we're not, the following error is much smaller. So see, the following error is much smaller. So let's go back to the original lambda and let's look at the Bode plot. So make this a 2 again. And now we're going to be looking at the Bode plot. So this is the desired closed loop transfer function, and I've already shown above that it's the same thing as if you have all the different terms, it simplifies down to this. And so I'm plotting it out, and you can see this is the response, and you can see there's no overshoot here because there's no zero, and there's the phase lag, and that's because the frequency response of the motion is about 1.5 hertz because it takes 1/3 of a second to ramp up, 1/3 of a second to ramp down. The sum of those two is 2/3 of a second, and if I invert that, it's 1.5 hertz. So I'm actually running the system right in here, so there should be just a following error. And then the bandwidth is 0.4 hertz or 25 radians per second, which is much better than the original 20. And then here is the two closed loop poles, and we got to remember that in reality there's actually a third pole, but it's canceled out by the zero, so it's not showing up. So if I go back to the other video or the other MathCAD file, and I go back down here, and again, a lot of this is identical, so I'm not going to repeat everything. You can see the bandwidth is a little bit higher on this one. Instead of being 4 point something, it's 6.4. And the reason why the bandwidth is higher is because of the zero. The zeros extend bandwidth, but they also can cause overshoot. And here you can see the 3 closed loop poles at -40, and then there's one closed loop zero at -22.857. And let's just scroll up real quick so you can see how that matches with how I calculated all this. Okay, these are the same parameters I have on the other worksheet, and here you can see the gain, the poles, and the zeros, and this matches what we had down below in the pole zero plot. So hopefully I was able to cover in 20 minutes or so what the instructor did, but a lot more. And the thing that I want to point out is that if you solve for the lead lag filters or the PIDs or PI or PEDs symbolically, then all you have to do is figure out what the open loop transfer function is, decide where you want to put the poles, plug the numbers into the equations for the controller gain and the other parameters like the poles and the zeros or PI or the P and the D terms, and you are done. You don't have to mess with all those angles, and actually they don't even provide a decent simulation given all the work that they've done. So hopefully you enjoy this and you'll find that symbolic processing is the way to go. Never use root locus again. I never use Root Locus. I always use the symbolic processing. Bye.